Swayam Prabha. Digital India. Educated India.
So, what I am saying is, this is your complete projection operator, gamma sum over R, gamma R, S dash T dash J star R hat. Yes, sir.
How R cap is represented, like where you written this R cap.
Yeah, so there is C3 operation.
So the matrix C3.
C3. So let us see. Let us say we are talking about the Px, Py, Pz orbitals, right? And we are talking about a C3 operation that is like this. So Px, Py, Pz, and this is your C3 operation. Then what will happen if you apply C3? Px becomes Py, Py becomes Pz, Pz becomes Px. So if you make this R hat operate on Px, the result you get is Py. This is only a matrix element, and here what you do is you actually make the symmetry operation operate on it, see what is the transform function you get, that is what R does, and then you simply multiply it by the symmetry operation, then you sum it over all R. But let me take a special case. So this is your, what will I call it? I will call it Pj S dash T dash, right? So what happens when I write S dash equal to T dash? You get Pj S dash T dash is equal to sum over R gamma R. What should I write now? This is J. What will I write? Can I write T dash or not? Huh? And what I will do is I will not take the trouble of writing the star anymore. The star was just to emphasize that you might have to work with imaginary matrix elements as well. Okay. So for now let me just go with this, not write the star. So consider that we are working only with real real quantities multiplied by R hat. Looking at this, how do you think you can simplify this a little more?
So what's the point of writing Pj S dash P dash if you are considering S dash is P dash?
You will see the point in a minute. So this is a subset of that, isn't it? See, right now what we have is, we have the complete projection operator. The trouble of working with the complete projection operator is that you will have to work this out for every S dash, every T dash, right? Each and every matrix element. And it is not as if it is not doable. So this is an example where they have done it. For point group C3V, what they have done is, they have taken the total matrix element and they have worked out the complete projection operator and made it operate on some arbitrary function xz plus yz plus z square, and they have shown what has happened. The trouble is that there are too many numbers here, so I want to make it a little simple. So let us see. So when you see something like this, gamma R T dash J, what is it that you are inclined to do? What is gamma R T dash? Diagonal elements. What happens if I add all the diagonal elements? We get the character. What is the advantage of having the character? You can use the character table. It's as simple as that. Okay. So what I'll do is I'll define Pj is equal to Pj S dash T dash summed over, sorry, what am I doing? Sum over T dash Pj T dash T dash is equal to, I think you will allow me to write, sum over R chi R of the jth irreducible representation multiplied by the symmetry operation. And to satisfy Shantanu, we are going to name this the incomplete projection operator. Incomplete projection operator. It is incomplete because you are not considering all the matrix elements. You are only considering the character. Okay, but that is an advantage, not a disadvantage, because say think of a 3 by 3 matrix. If you work with the complete projection operator, then per matrix how many numbers would you have? 9, right? Instead of that, if you work with the character, how many numbers would you have per matrix? 1. Only the character, right? That is the advantage of using an incomplete projection operator, and it does the same thing. So remember, this is what is going to be very useful for us for the rest of our course. Pj equal to sum over R chi R j R hat. If it's C3V, for the first basis A1, Z is a basis. For A2, RZ is a basis. So the fun here is this. See what they have done. We will also work this out, but using the reduced. Can you read? Now see what they have done is they have worked with the complete projection operator. For that they need all the matrix elements. Okay. With that they are working with some arbitrary function xz plus yz plus zx. This is what I was saying, linear combination. Okay. So they are working with this linear combination xz plus yz plus z square. Let us quickly look at the character table and see where they belong. Where does xz belong? Xz and yz belong to E. Can you see or not? C3V? Xz and yz jointly form the basis for E, right? So xz has E symmetry, yz also has E symmetry. What about z square? Z square is A1. Okay. So they have taken a sum of linear combinations of 3 terms, 2 of which have E symmetry and z square has A1 symmetry, and they have made this projection operator operate on it. Okay. And then since they have worked with whole matrices, they have a lot of numbers. We will have a little less numbers. They have done that, and see what they have got. Oh, so what they have done is they have used P11E. So you have to do it for every matrix element, isn't it? So this is P11E. They have used that, and they have got the coefficient of xz to be 1, coefficient of yz to be 0, coefficient of z square to be 0. So on and so forth, they have done all this. And finally they see that the coefficients of xz and yz are non-zero, whereas the coefficient of z square is 0. But the problem is that it is a longish route. Okay. Let us use the incomplete projection operator on the same thing.
Coefficient of z square is throughout 0.
Let us use the reduced one. There it is throughout 0, yes. Okay. Let's take this now. So this is your this is the expression of the incomplete projection operator. It's the only difference is that they want to keep Li and Li by H, and I am not interested. Sum over R chi R j R, right? Now I want to use this on xz plus yz plus z square. Want to work this out? P superscript j hat is equal to sum over R chi R of j R hat. So what I want to do is, for C3V, I want to use PE. Got it? You understand what's the meaning of PE? Projection operator corresponding to the E symmetry species, EIR, E irreducible representation, the third one, the two-dimensional one. Okay? Got it? So what will that be equal to? Two R hat. What is the character of E? What is the character of identity in the E representation? Character of E in E could be confusing. Identity in E representation. 2. So instead of chi E in the E representation, I have written 2, right? In fact, I can take the R out also, maybe. No, I cannot. 2R plus, what is the character of the second one? What is the second one? C3, what is that? So I will write E, 2E, something like this. Instead of R, I should also, otherwise you will get confused. E. What is the second one? C3 is minus 1, right? So minus 1 into C3. What will be the next one? No. It will be minus 1 into C3 inverse or C3 square. Do not forget 2C3 means C3 and C3 square. They belong to the same class. That is why they have the same character. So they are written together in the character table. But in applications like these, you have to consider C3 as well as C3 square. Understood?
So their projections will be different.
Yes. Of course. See, think of x once again. X you rotate by 120 degrees, you will get some x intercept, some y intercept. If you rotate by 120 degrees more, the x intercept, y intercept will be not intercept, x component, y component will be different, no? So it's definitely going to be different. So let me write it in a little less untidy manner. 2E hat minus C3 plus hat minus C3 minus hat. Or I could have just written C3 and C3 square. This is what I have to operate on xz plus yz plus z square. Okay? Can you do this and tell me what you get? Let us see. 2E operating on xz plus yz plus z square is equal to what? 2 into xz plus yz plus z square. C3 plus operating on xz plus yz plus z square. What will it be? C3 plus operating on z is z. C3 plus operating on z square is z square, right? Because C3 is along z direction. So all you have to consider is how this x and y transform, isn't it? So what will it be? C3 plus operating on x, what do you get? Minus half into x plus root 3 by 2 y. I will just write the z's. Okay. Then, so xz is taken care of. Then, what about yz? How does y transform? Plus half xz, then plus half xz, y. Y, how does y transform? Y has that root 3 by 2 x, isn't it? Okay, I am not very good at remembering these things, so you need to help me here. Minus root 3 by 2 xz, then minus half yz. All I remember is the character is minus 1. Okay, so diagonal elements have to be minus half and minus half. And then where it is plus root 3 by 2, where it is minus root 3 by 2, I have to work out. Okay, so this is done, and then z square, I leave it as z square. Fine, and then C3 minus operating on xz plus yz plus z square. You can work that out? Can you work that out or not? Huh? So just work it out and satisfy yourself that this is what you are getting. See, they have worked it out here. See, what is the advantage? Well, we will come to the advantage. Once you work this out, finally this is what you get, xz plus yz. All the terms in z square cancel off. Okay. So what have I done essentially? I have taken a linear sum of 3 terms, 2 of which have E symmetry and the third of which does not have E symmetry. When this incomplete projection operator corresponding to E symmetry operates on this linear sum, what it does is that it annihilates the term that does not belong to that symmetry species and it retains the term that belongs to that symmetry species. So it projects the terms with the desired symmetry. That's why it's called the projection operator.
Here the coefficients are 1.
Huh.
Will always they be 1 if they belong to that?
No, no. It depends on what you need. If you need them to be normalized, like what we need our SLCs to be, then you work out the coefficients. And it could have been 2xz plus yz or 2xz minus yz also. But that, let us not get into that. Do we get the crux of the matter? Huh? That I have taken a mixture of terms belonging to two different symmetries, and when I have used the projection operator corresponding to PE, then the term that is not PE, not E symmetry, that does not have E symmetry gets annihilated, and the terms that have E symmetry survive. So that is the magic of projection operators.
So if you have to take xy in this one, both the coordinates get transformed, can we take it as a product of the two transforms?
Yeah, yes. That we worked out, right, once. Direct products, when we talked about direct products, that's what we did. Alright, are you all okay with this? Huh? So now we have got Aladdin's genie. Now we can do whatever we want.